Okay, so in this problem we have block A, which has a mass of m, and we're told that it's able to slide within a smooth inclined slot, and that a spring of stiffness K is attached between A and a fixed point O as shown in the figure. A constant horizontal force F acts on the block, and the system is released from rest at position 1, where in position 1 the spring is perpendicular to the slot and is unstretched. We're told later at position 2 block A is directly above point O. Based on this information, and assuming that block A reaches position 2, we're asked to determine the speed at the block at the second point. We're asked furthermore to told that if A does not reach position 2, to explain why not. Okay, so to help us out here, I'm going to go ahead and draw a free body diagram for this system in an arbitrary orientation. I'll do so treating it as a particle. And so if I do this, I know I'm going to have a normal force acting on the system. And in addition, we're in a smooth slot, so I don't have to worry about friction, but I will have weight. I'll have the force of the spring. And actually, that's going to be it for us. We know that the normal force is not going to do any work, but the weight in the spring can be accounted for in the potential energy, and I forgot to put in here my force F. The force F, of course, is an applied force, and this will be one that we do have to account for in the non-conservative work term. So with that being said, we know we can express the work-energy relationship for the system as T1 plus V1 plus the non-conservative work done and moving from state 1 to state 2 is going to equal T2 plus V2. And if I make some substitutions here, I'll first of all have T1 is equal to 0 because we're released from rest. V1 is going to be the potential energy of the system at the two states, or I should say in this case the first state. Let's define our gravitational potential here to be 0. In this case, V1 is initially going to be 0 because we're at the datum and the spring is unstretched. The non-conservative work done in moving between states 1 and state 2 will be actually in this case proportional to the amount of distance traveled and the force, so we know this is going to be the integral of F dot with dr. And in this case, we know this is going to be the integral. F is a constant force in the I direction. I'm going to dot that with the differential displacement, which in this case is dr times the projection, which will be in this case the cosine of the angle theta in the little I, plus the sine of the angle theta in the little j. And so if I go ahead and integrate this here, what I'm going to end up with is that I'll have F times d times the cosine of the angle theta. In terms of potential energy at the second state, we have a particle in translation, so we're going to have 1/2 times mv2 squared. And in terms of potential energy at the final state, we're now above the datum, so I'm going to have m times g times d times the sine of the angle theta, plus the amount of stretch in the spring, which is going to be plus 1/2 times k times delta squared, where delta is the amount of stretch at the final state. So if we want to determine the amount of stretch at the final state, I can do that quite easily. In this case, it's going to be m times g times d times the sine of the angle theta, and the amount of additional length we'll have in the spring here will be equal to, in this case, d times the sine of the angle theta, and that'll be squared. So if I substitute these 5 expressions back into the work energy equation, what I'll have is that F times d times the cosine of the angle theta is going to equal 1/2 times mv squared plus mg times d times the sine of the angle theta plus 1/2 times k times d squared times the sine squared of the angle theta. From here, you can go ahead and solve this equation for V2. If you find out that you can't find a numerical value for D2, you know that the system never actually reached that point. But I'll leave it up to you to determine if that's true or not, and wish you the best of luck. Take care, everyone.